Hello everyone. In this video we're going to be looking at graphing quadratic functions. This is part one of a two-part series, and in this video we'll be looking at graphing quadratic functions in vertex form, and in the next one we'll look at how to deal with functions that are given to us in standard form. We've already discussed the fact that any function written in this form, ax squared plus bx plus c, where a, b, and c are just real constants, and of course a shouldn't be 0 because otherwise the square term or the second degree term disappears and we just get a linear equation. So that's the reason for the restriction. Any function that's written in this form, that can be written in this form, is a quadratic function. It may not exactly be in that form, but if we manipulate it and we can eventually put it in this form, then we consider it to be a quadratic or second degree function. The highest degree term in this function is the square term, so that's why it's called the second degree function as well. If you recall, when we were dealing with linear or first degree functions of this form, f of x equals mx plus b, where m and b were just real numbers, and of course m shouldn't be 0 because then we just break down to a constant function. The graphs of these kinds of functions we call the line, and the graph of quadratic functions of this form we call parabolas. And we're going to learn quite a bit about parabolas in this video. This form here is called the standard form of a quadratic function, and in general, whether it's linear functions we're dealing with or quadratics, standard forms are really powerful for classification purposes, but are usually not the most useful or efficient form to use when it comes to applying them or graphing them. So we took much of elementary algebra to master linear functions and their graphs, and in this class we spend most of our time with quadratic functions. So we'll start by looking at some real simple examples, and we'll work our way up to more complex ones. If you recall from elementary algebra, when we dealt with linear equations, the most efficient form to use was the slope-intercept form, and we again use the standard form ax plus by equals c for classification, but we really depended and relied on the slope-intercept form to help us quickly graph linear equations. As it turns out, quadratic functions have their own most useful form, and that's called the vertex form. The reason why it's called that is because just by looking at it, the most important point of the parabola, which you can see here, it's either going to be the lowest point if it's a upward facing parabola, or if it's a downward facing parabola, it's going to be the highest point of the parabola. And you can see that most important point just by looking at the equation written in the vertex form. HK will be the vertex, and also there is this imaginary line that cuts the parabola exactly in half, and the left and right sides of that imaginary line, which is actually not part of the graph, but we draw it here for visualization. The left and right parts will be mirror images, with displaying the role of the mirror. So we call that imaginary line the axis of symmetry, and that also obviously it's going to just be x equals h. So again, we can see that in our vertex form of a quadratic function or a second degree function. And we're going to be dealing with all of these letters in a minute in actual examples, which will make more sense. Okay, in our first example, we're going to look at what can be considered to be the most important parabola, because this parabola here whose graph is the equation of f of x equals x squared is what we consider to be the reference parabola. So when it comes to any other parabola, we're going to be comparing it to this reference parabola and, for example, discuss whether it is wider than this parabola or narrower than this parabola, or its location is higher or lower, etc. So we're going to be comparing all other parabolas to this reference parabola f of x equals x squared. Of course, we can easily make a table of values here. As far as how many do we absolutely need, the answer would be 3. If you recall, with lines, we used to say 2 points determine a line. That means if you have 2 distinct points in a plane, there is one and only one line that will go through those 2 points. Well, with parabolas, it's actually 3 points that are required. Usually, as I mentioned before, it's going to be the vertex and 2 other points which we will find in a very strategic manner. And the other points we're just putting here for reference. So if we just start at -2, we know that if we square -2, remember quantity -2, so the negative is going to get squared 2, we get 4. With -1, we get 1, 0, 0, 1, 1, 2, 4. You can see the symmetry of this parabola very distinctly here. Here is the line of symmetry, which, if you notice, is the y-axis itself, which is going to have the equation x equals 0. And notice that we can also easily put this into the f of x equals a times x minus h squared plus k form. And we notice that in that form, our a is going to be 1, h is going to be 0, and k is going to be 0. So we can see that 0, 0, hk is the vertex. And notice that the value of a here is exactly 1, and whenever the absolute value of a for any parabola is going to end up being 1, then that parabola is going to have exactly the same width as this reference parabola. When this a, when we say absolute value of a, because sometimes there will be reflections of this downward with respect to the x-axis or whatever axis will go through the vertex, whatever line, horizontal line will go through the vertex. And because of that, notice that whenever the absolute value of this constant that's multiplied in the beginning here is greater than 1, that's actually going to end up giving us a parabola that is vertically stretched, so it'll actually end up looking narrower than this parabola. And whenever the absolute value of a falls between 0 and 1, we don't want to just say less than 1, because that would include negative numbers. We know absolute value is never negative. So whenever that happens, that's actually going to vertically compress it, and you'll actually end up getting a parabola that is wider than this one. So we'll be looking at these in a minute. So we discussed the axis of symmetry, which is just the y-axis, whose equation, as we know, is x equals 0. Notice also that this parabola opens up. That always happens when a is greater than 0. And when a, this constant here, is less than 0, we're going to be seeing a downward facing parabola. Now, as far as the domain, which is the set of x values that are in play in creating this graph for us, or all the inputs of this function, there are no restrictions. We can use any x value, so the domain is actually the open interval from -infinity to infinity, which basically just means the entire set of real numbers. This is given here in interval notation, and we're giving the same set here in set builder notation. And but the range, which is the set of all the y values or outputs, notice you're not, because of the squaring effect here, you're not going to get any negative outputs. So the range is going to be all real numbers that are greater than or equal to 0. So we write it in this manner in interval notation. Now be careful in the set builder notation. Here you'll want to say y belonging to R such that y is greater than or equal to 0. All right, next we want to look at what are called horizontal translations or shifts of the graph of y equals x squared. So here we'll look at three different functions. In the middle in red, we have y equals x squared. On the right here, we have y equals x minus 1 squared. And on the left, we have y equals x plus 1 squared. So you'll notice that depending on the value of h, you'll either be moving to the left or to the right. So this is a little bit confusing for some students because they see x plus 1 and they think, oh, this should move to the right. But notice that vertex form requires us to write it as f of x equals a times x minus a number. So when you want to write x plus 1 as x minus a number, that number is going to have to be negative 1. That's what makes h equal to negative 1. So the easiest thing to remember is that when you have x plus a number as opposed to just x squared, you're going to actually be moving the graph of x squared to the left that many units. And when it's x minus 1, notice h just becomes 1. That's the translation factor constant. And in this case, you're going to be moving 1 unit to the right. Now, if you look at the tables, notice that in each case, the first thing we want to do is we want to find out what makes this 0, which gives us the h. So here, for example, for x plus 1 squared, we know that negative 1 will make x plus 1 0, right? So then all we need to do to get a really solid graph is we have to just go, as far as the x values are concerned, we're going to pick an x value that is 1 unit to the left of the x coordinate of the vertex, and then we'll pick one unit to the right. Here we're utilizing the symmetry of the parabola to get a good graph and to get 3 very easy points that are going to help us get a very good picture of the graph with very little effort. So notice that when you plug in negative 2 here, you get negative 2 plus 1, which is negative 1, and then you square that, you get 1. Negative 1 will give you 0, you square that, you get 0, and 0 will give you 0 plus 1, which you square to get 1 again. And as we expected, because we went the same distance to the right as we went to the left. And we can do the same thing with this. Notice this time we look to see to find our vertex. First we go ahead and try to make that 0. We know that's going to take x equals 1. So we start in the middle by finding the vertex. Then we simply, on the input axis or the x-axis, we go 1 unit to the left and exactly the same amount to the right. So 1 unit to the left of 1 is going to be 0. 1 unit to the right of 1 is going to be 2. So we go ahead and calculate those, and here we get these 3 points that are going to help us graph this function given here in green, which is the right shifted parabola. Notice that in both cases, a is 1. Actually, in all 3 cases, a is 1. So notice how they're exactly the same width. There's no change in width. And what is going to change is the location of the vertex, and that's the only thing that's changing here. These are, imagine the red graph being made of wire. You're just either grabbing it, pulling it to the left, or pulling it to the right. That's all you're doing. Notice also the domains for all of them remains to be the set of real numbers. There's no number you cannot use for x here. And the range also happens to be the same for all of them, because look at all the y values that you have as outputs for either the blue, the red, or the green graph, and you'll see that all of them take on y values that are 0 or higher. So that's how we know that. All right, so that's basically just a simple horizontal shift or translation of the graph of y equals x squared. Make sure you pause this, spend some time on this screen till you fully understand it, and then proceed. Do notice that what is changing from this to become this or this other one is the x value itself. So that's why we end up with a horizontal change or shift. So the change is coming at the input level, right? So until we get to the next screen, keep that in mind, and then you'll see why that matters. All right, now observe how in these two cases, again, we're putting all three on the same graph for comparison. Notice that x is not changing. The x squared part is the same, right? So it's not the x that is changing, but the entire x squared, the change is happening at the y level. We're taking this y equals x squared, and we're either subtracting one from it or adding one to it. So here what's going to change is the elevation, the y value. So notice with y squared plus with y equals x squared plus 1, you're just taking the graph which is in red, which is our reference graph x squared, and you're pulling it up 1 unit. With y equals x squared minus 1 depicted here in blue, you're taking the red graph and you're moving it down 1 unit. Now notice that if you put this graph or that one in vertex form, you'll end up with something like this: y equals 1 times, you can always write x squared as x minus 0 squared plus a negative 1. So your h here is going to be 0 and k is going to be negative 1. We know that the vertex is always hk, which is going to be 0, negative 1. So for x squared minus 1 in blue, the vertex moves from 0, 0, which is the vertex for the reference graph x squared itself, and it goes down to 0, negative 1. And for the green one, notice that if you write it in vertex form, you end up with this. And so h is 0, k is 1, so the vertex moves to 0, 1. Now notice, for example, if we consider, say, the blue one, x squared minus 1. We just mentioned that the vertex is at 0, negative 1. So we always, when we want to make our table, we start there in the middle. Then from that x value, we go 1 to the left and then 1 to the right. Compute those, and then we'll have the 3 points that we need to get a really good graph of the parabola. And notice the same thing here. Notice that we start at the vertex, which is 0, 1, then we move 1 to the left and 1 to the right, and we end up with the points that we need to graph the green curve. And these here are called vertical shifts. Notice there's no change in shape. All you're doing is you're taking the red graph. Again, imagine it's made of wire and you're pulling it up 1 unit, or you're grabbing it and pulling it down 1 unit. So that's all that's happening here. Now do notice that while the domains continue to be the set of all real numbers, the ranges are different here. Notice that the outputs of the green curve here, which is y equals x squared plus 1, there are no outputs below 1. So the range is going to be all the y values from 1 and up. So that's why you see the range of that function being closed interval, half closed interval or half open. You can say half open or half closed, because on this side it's closed, but on that side it's open. So it's the half open interval 1 to infinity. Notice 1 is a possible output, so it's included. That's why we use the bracket. Now for the blue graph, notice that the outputs begin at -1. We have y values starting at -1 for various points on that graph. And also we see that all other points above that will be possible outputs as well. So the range for that one, which is the set of all the outputs, because notice here we just show a few nice ones, but you also get all, kinds of decimal and irrational outputs as well. So the range for that one will be bracket -1 comma infinity. If you wanted to write that in set builder notation, you would say all y such that y is greater than or equal to -1. For this one, you would say all y such that y is greater than or equal to 1. Again, these are vertical translations or shifts of the graph of y equals x squared. Spend some time on the page, make sure you understand it, and then we'll proceed. Okay, the next kind of transformation of the graph of y equals x squared that we're going to look at are going to be vertical stretches, which once they take place, they actually end up looking like horizontal narrowing. So, for example, when you look at the green graph, notice that the red graph is our reference graph y equals x squared. So when you look at 2x squared, basically all the outputs of x squared are going to get doubled. Notice the same input, -1, the output here is doubled. 2 times 0 is of course 0, that doesn't change, but notice for the input 1, 1 squared is 1, but 2 times 1 squared becomes 2. So basically all the outputs are getting doubled for the green curve, right? So notice that's called it's as if you're taking the graph and you're just pulling it up like this. So it's a vertical stretch, but when you look at it horizontally, notice it actually looks like it becomes narrower. So a vertical stretch of a parabola ends up visually looking like a horizontal narrowing. So this is why we said when a, which here notice is 2, ends up looking narrower than the graph of x squared itself, where a is 1. And for 1/2 x squared, the opposite happens. Notice that's an actual vertical compression. It's like you're pulling it down, right? But when you look at it horizontally, notice it doesn't look like a compression at all, does it? It looks like a widening, but that's just because of the way this effect happens to work out. So, but a lot of people are confused about this, and unfortunately, I've even seen some teachers explain it incorrectly. So the actual correct terminology here would be a vertical compression right here. But notice that the overall effect is that it looks, the parabola, when the coefficient here is between 0 and 1, ends up looking wider than the reference parabola. Remember, we're always comparing to the reference parabola. You always have to have a reference to compare to. Like with lines, that was the line y equals x. So when we wanted to say steeper or less steep, we always compare to the line y equals x. For parabolas, it's y equals x squared. Okay, so the general category that all these fall into is actually called vertical dilations. And so remember, when the coefficient is larger than 1, the parabola is actually going to look narrower than y equals x squared, and when the coefficient is between 0 and 1, the overall effect is that the parabola is going to look wider horizontally. Now, as far as where these come from, again, notice that when you put them in vertex form, all of them are going to have 0, 0 for the vertex. Notice. So the vertices are all the same, and also notice that the domain and range will be the same for all of them. So they are very similar in that case, because you're just bringing about a change in the vertical direction by either doubling the outputs or halving the outputs. But the reason you don't see any change here, because of the particular nature of 0. All right, so these are called vertical stretches and compressions. The general category for all of them called vertical dilations. All right, the last type of transformation we're going to look at is actually probably the simplest one. That's when you basically just flip it over vertically, and these are called vertical reflections of the graph of y equals x squared. So notice that basically, because you're multiplying by -1, all the outputs of y equals x squared itself are going to become the opposite of what they were. So that's why there's this reflection effect. And now when you put them in vertex form, both of them, notice you still have 0, 0 for the vertex, but do notice that the domain and range do change, because obviously the domain of the blue graph, which is y equals -x squared, is still going to be all real numbers, but the outputs, notice they start here and then they go down from there. So the outputs, the set of all the outputs is going to be -infinity to 0, and that's inclusive of 0. That's why we need the bracket. So be cognizant of that fact, and because of the fact that the absolute value of a is 1, that's a typo there, that should be the absolute value of a. So let's fix that. That's a good thing about having this pen situation here, so we can fix it right away. All right, because of the fact that the absolute value of a is the same, notice that the width is the same for both of them. There's no change in width. All right, and that's the last type of transformation. All of these translations, dilations, reflections, these are all called transformations of the graph of this particular function. And the nice thing about it is that once you learn these transformations, they apply to all functions. So it's a much more general situation than what appears to be right now. All right, so here I wanted to do a summary of all these things we just learned about, and for the purposes of this table, let h, k, and a all be positive so that this will make sense. So let's say that you know what the graph of x squared looks like, which we do, right? It's just a reference y equals x squared. So here we say to obtain the graph of, for example, this function for some value, positive value h, you're going to move the graph of x squared h units to the right, correct? Remember, these are just horizontal translations. To get the graph of y equals x plus h squared, you're going to move the graph of y equals x squared h units to the left, remember? Now, here, this is when you're just going to take the entire graph and move it up or move it down. So these are the vertical translations. So to get the graph of this kind of a function, you're just going to take the graph of y equals x squared, which you know would be right there, and you're going to move it k units up For this one, you're going to take the graph of x squared, which is right there, move it k units down. These are the vertical stretches. Now remember, if the absolute value of a is greater than 1, it's actually going to become narrower. And if the absolute value of a falls between 0 and 1, it's going to become wider. And lastly, we have the reflection. So if we have ax squared looking like this, we know that negative ax squared will just reflect with respect to that horizontal line which goes through the vertex. And remember, this vertex may not be at 0, 0. We'll look at those situations soon. All right, so now we can put it all together and look at some interesting problems where different kinds of transformations are involved. We can notice here, for example, we have a which is not 1, we have h here, k here. So we're going to graph this in two ways. One is we're going to go old school, and we're going to plot it using points. Here, one of my numbers got left out. I think it got hidden behind the other graph. So here I'll just add it. All right, so notice that this is given to us in vertex form, which is nice. Next section, we're going to look at what happens if it is not given to us in this form. But in this section, we just want to be able to handle these basic transformations. So remember, when we want to create our table, the first thing we're going to do is we're going to find h, which is going to be the x coordinate of the vertex, and we get that by just the easiest way to do it, just set this equal to 0. So when you solve that, you get what? You get x equals 3. So we know that's going to go in here. Of course, when you plug in 3, you get 3 minus 3 is going to 0 out. So that whole term becomes 0 plus 4. So you get 3 fourths. So you start in the middle here. And then you pick an x value exactly 1 to the left of that x value, and you pick exactly 1 unit to the right. That's going to be the 3 strategic points. So the thing about these tables that makes it difficult for some people who are used to graphing lines, for example, is that they just want to start with 0, 1, 2 or something like that. You cannot just choose random points and expect to get a good graph, because if you did 0, for example, here, you would be, look at the piece of this graph that you would be graphing. It would be something completely nonsensical. You would have just a portion looking like this up here. That would not do you any good. So what you want to do is you want to make sure that you start with the vertex, and then just and you know, whether you go 1 unit left, 1 unit right, or you want to go 2 left, 2 right, doesn't matter. Just go the same distance, and you'll use the symmetry to get 3 really nice points to graph the function with. And so that's just by plotting points, which is very efficient, very fast, and you can see that the axis of symmetry is always going to be x equals h. So in this case, it's just going to be this vertical line, x equals 3. The vertex is, of course, 3, 4. And the domain is obviously still all real numbers. There's no x value that you would get in trouble plugging into here. So this is just a nice polynomial function. So no problem with any inputs. But however, notice that the range, the outputs, they start right here and further up from there. So the range of this function is going to start at 4 and then go up from there. So notice that a here, 2, that tells us whether it's going to open up or down, and also it's going to tell us if it's going to be narrower or wider, or as wide as x squared. And of course, since this is greater than 1, we know it's going to be narrower than y equals x squared. All right, so that's doing it by plotting points. The other way is by just looking at this and deciding what transformations you need to do to the graph of x squared to get this graph. So you can start by taking care of the horizontal shift. So you say start with the graph of x squared, then move it 3 units to the right. Remember, x minus 3 turns out to be a movement of 3 to the right. If it were x plus 3, because it would have been x minus negative 3, that would have been a shift to the left. So, but here we have x minus 3, so we start with the graph of x squared, we move it 3 units to the right, then you can take care of the vertical shift, then you're going to go 4 units up, right? And that brings you here. So you've taken the graph of x squared, you've moved it 3 units to the right, 4 units up, but that's not all. Now you have to take care of the vertical dilation. So we know that this is 2, so we know that we need to go ahead and make this narrower. We're going to vertically stretch it by a factor of 2. And of course, we know that visually that means that the parabola actually becomes horizontally narrower. And that's how you would attack a problem like that. Make sure you understand that before we move to the next one. Okay, for our final example, we're going to look at another function which involves 3 different transformations of the graph of y equals x squared. Again, we'll do it in 2 different ways. One by just plotting points, and we'll also do it then visually by just moving the graph of y equals x squared to obtain this graph. So to start off by just finding the right points, remember, we're going to start by setting this equal to 0, x plus 1 equals 0, which gives us negative 1. So that's going to be the first x value that we substitute. Now, when we plug that in, we get 0, that goes away, so we get minus 3. So that's where this negative 3 comes from. Then remember, we go 1 unit to the left of negative 1, and that'll bring us to negative 2. And 1 unit to the right of negative 1, which brings us to 0. So notice that when you plug in negative 2, you end up with negative 2 plus 1, which is negative 1 squared. That's 1 times negative 1/2 will be negative 1/2 minus 3. So that's negative 3.5. That's where the negative 3.5 comes from. Now, you know, because of symmetry, this should give you the same thing, right? But never trust that, because you may have made a mistake here, right? You should always go ahead and just substitute it again. So 0 plus 1 is 1, squared is 1, times negative 1/2 is negative 1/2, minus 3 does indeed give us negative 3.5. So if these don't agree, that means something went wrong. Because of symmetry, this should happen, correct? All right, so then you just plug in, plot those points, and you draw your parabola. So easy enough. Of course, you can see that in this format that we have, h is going to be negative 1, so, and k is going to be negative 3. So we know the vertex is at negative 1, negative 3. The axis of symmetry will be right here, which is always x equals h. So x equals and negative 1 will be the axis of symmetry, and that's all there is to that particular method of graphing. Of course, the domain will be all real numbers. The range is actually gonna end here. So you start at negative infinity, but the y values that are outputs of this function, they stop right there. So that's why you go up to negative 3. Notice that the a is negative. That's why we have this downward looking parabola. Also look at the fact that the absolute value of a is between 0 and 1, and you know that while that means vertical compression, it actually horizontally will end up widening the graph. So what it does vertically and horizontally are the exact opposites of each other. All right, so that's the method of plotting points. Now, if we just want to talk about, we don't look at any points, we just want to say, all right, start with the graph of y equals x squared and then do what to it to get this graph. All right, so we'll first start with the horizontal shift. Now we know that this is x plus 1, and we know that means a shift of 1 unit actually to the left when it's plus, right? So we start with the graph of y equals x squared. We move it 1 unit to the left. Then we can take care of the vertical shift, which means we need to go 3 units down. So starting here, we go 1 unit to the left, 3 units down. Then we're going to make it wider because of the 1/2, right? And also because of the negative, once we're done with all that, we're going to flip it over, always with respect to the horizontal line which goes through the vertex. And that's how you would end up with the exact same graph that we obtained by actually plotting points. So you have basically learned 2 ways of graphing these quadratic functions in vertex form. One way is to quickly find 3 relevant points, and these are not random at all. Remember, you start with the vertex, then you find an x value, exactly 1 point to the left of the x value of the vertex, and 1 point to the right, 1 unit to the right of the x value of the vertex. Then you find the corresponding y values, and you have the 3 magic points that are going to help you get a really nice picture of this parabola. The other way, of course, is by doing the various transformations which you have studied in this video. All right, so that should do it for us. Make sure you practice these. You can always create these functions and then check them on a website like Desmos to see if you've done it correctly or not. So make sure you do that until we meet again. Stay safe.